Now, cell potentials, one thing you have to realize is that they do depend on the reaction quotient. That's why I kept emphasizing standard conditions in the previous slides. Okay, so, and the way they depend on the standard condition is given by the Nernst equation. Cell potential is equal to whatever the standard cell potential is minus RT over NF times the natural log of the reaction quotient. This is the same reaction quotient we talked about when we talked about equilibrium. Okay. Now, at room temperature, which is 298 Kelvin, okay, then the cell potential is equal to the standard cell potential minus this RT over NF, okay, and then if you change instead of a natural log, you take the base 10 log, this expression becomes 0.059 over N. So that's called your Nernst equation. What's the importance of this? This will allow you to determine what the voltage is going to be. If you were to set up, okay, your two half reactions in separate compartments, and you measure the voltage between them, that's what this E cell is. The cell potential is the voltage that you can get out of your battery when you set up your half reactions in separate compartments. Okay, so for non-standard conditions, your cell potential will be positive for the spontaneous reaction. So you know which reaction will be happening as your battery discharges. So when you say your battery is discharging, what's happening? As a battery discharges, the electrons come out of the negative terminal and go to the positive terminal, right? So that's a sign of a reaction going on inside the battery. Okay, so as it discharges, its voltage is going to be changing. So that cell potential is going to be changing. Why? Because your reaction quotient Q here will be changing. Okay, you'll be forming more products, right? So eventually, when it's fully discharged, your cell potential will have reached, your reaction will have reached equilibrium. What happens to the cell potential at equilibrium? It becomes zero. Okay, so when you have a dead battery, it's no use to you, right? So let's predict if this reaction is going to be spontaneous or not. If your silver ion concentration is 0.01 and copper is 0.01, we'll just assume those are your 0.1. Let's assume those are your activities. What do we need to do here? What did we say was the standard cell potential for this? We did this earlier. Copper ion plus silver. This one. We knew it wasn't spontaneous under standard conditions, and we found that cell potential to be negative 0.46, right? So our standard cell potential for this, we found it earlier to be negative 0.46 volts. How do we solve for the actual cell potential? If we're not at standard conditions, we're going to say it's E naught cell minus 0.059 over N, okay, log of the reaction quotient. What's our reaction quotient here? Remember how to construct reaction quotient? Products over reactants. What's the activity of copper solid? Activity of a solid is 1. What's the activity of an ion in solution? That's the concentration of silver. Okay, divided by activities of the reactants. By the way, coefficients here are 1 and 1, so you raise this to the power 1. Activity of silver is 1, metal, solid. Activity of copper ions would be concentration of copper ions. All right, so that's how you do that. So what's our standard cell potential? Negative 0.46 volts plus 0.059 over N. What is N? N is the number of moles of electrons transferred per mole of reaction. Okay, so let's go back to this expression right here. How many electrons are transferred per mole of reaction? 2, right? This happens twice. Every time this happens once, your reduction of your oxidation of your silver happens twice. So 2 electrons transferred. N is the number of electrons transferred in your balance equation. Let's take a look at this equation right here. Here's your way to figure out your N. From copper plus 2 to copper, that's 2 electrons gained. Okay? There should be a 2 there. I forgot the 2. It's not balanced. To balance it, you need the 2 there, right? And that's 2 electrons lost. So N is equal to 2. So if N equals 2, so I divide that by 2, and then take the log of, what's your silver concentration? That makes a big difference now. There's a 2 there, so that should be squared. Okay? And your silver right here should be squared, but 1 squared is the same thing. So log, what's the silver concentration? 0.01. So that's 0.01 squared divided by, copper concentration is 0.1. So that's 0.1 right there. So our cell potential is negative 0.46 volts plus 0.059 divided by 2 log of, what would this be? That's 10 to the negative 4 over 10 to the negative 1. So that's 10 to the negative 3. Okay. What's log of negative 3? It's negative 3. Okay. Log of negative 3. Negative 3. Take the log. Oops. 10 to the negative 3. 1 times 10 to the negative 3. Take the log. It's negative 3, okay? The log of 10 to the x is x. Okay, so this gives you how much? Negative 3 times 0.059 divided by 2. That's negative 0.0885. And this is negative 0.46. So just keep those sig figs there. So even more negative. Negative 0.55. Okay? Volts. Even less spontaneous. So the reverse would be even more spontaneous. So if the forward reaction is non-spontaneous, that means the reverse is non-spontaneous. So if you set this up as a galvanic cell, okay, where you separate your reduction and oxidation, you're still going to get a current, but not the way you would expect it. It's the other reaction that's going to happen. You're still going to get a voltage between them. And so we're going to talk about galvanic cells next time. Okay? I think that's what the next slide is all about.